Hello, my name is Magnus Petersen. This is a tutorial on TensorFlow where we will make a simple linear model. It is assumed that you are familiar with basic linear algebra such as matrix multiplication, and that you are familiar with Python programming and the Jupyter Notebook editor. We will use matplotlib to show plots, and TensorFlow and NumPy, and then we will use the confusion matrix from scikit-learn. First we load the MNIST dataset. It is about 12 megabyte, and if you don't have it already, it will be downloaded automatically. You can set the path for the dataset here. The dataset consists of 70,000 images, and it has been divided into a training set with 55,000, and a test set with 10,000, and a validation set with 5,000. We don't use a validation set in this example. When we load the dataset, we set one hot to true, which means that it is loaded as one hot encoded. This means that the label of each sample in the dataset is a vector for the number of classes, in this case 10, and all the numbers in each vector in each row in this matrix shown here are 0 except for the class number. In this case it is 7. And in the second row the class is 2, and in the third row the class is 1, and in the fourth row the class is 0. And in the fifth row, the class is 1, 2, 3, 4. We also need the class numbers as regular numbers, so we calculate that here, and we can show them here. For the 5 samples shown above, the classes are again 7 to 1, 0, 4, and this corresponds to the one hot encoded vectors up here. Here we define some variables or constants for the data dimensionality, and the images in MNIST are 28 by 28 pixels. And there are 10 classes, one for each digit. This is a helper function for plotting images, and it creates a figure with 3 by 3 subplots, and then it goes through those subplots and shows the images. Note that the images are stored as one-dimensional vectors, so we have to reshape them into a 28 by 28 pixel image. So let's plot a few images from the test set to see if the data is correct. So we plot the first 9 images, and we have here the true classes for each of those images. So the first image shows a 7, and the true class is indeed a 7. And the second one is 2. Third is 1, 0, 4, 1, 4, 9. And then we have one that looks a bit strange. The true class for this image is 5, but this image actually gives problems, as we will see below. So the entire purpose of using TensorFlow is to have a so-called computational graph. And this can be executed much more efficiently than if the same calculations were to be performed directly in Python. And TensorFlow can also be more efficient than NumPy, because TensorFlow knows the entire computational graph, whereas NumPy only knows each operation at a time. Another key purpose of TensorFlow is that it can automatically calculate the gradients, which are needed to optimize the variables of the graph so as to make the model perform better. This is because the graph is a combination of simple mathematical expressions, so the gradient of the entire graph can be calculated using the chain rule for derivatives. TensorFlow can also take advantage of multi-core CPUs as well as GPUs, and there's now even a special chip for TensorFlow which is called the Tensor Processing Unit. So a computational graph in TensorFlow consists of the following parts, which we will go through one by one below. So it has placeholder variables, and these are used to change the input to the computational graph. Then it has model variables that are going to be optimized so as to make the model perform better. And then there is a model, which is essentially just a mathematical function that calculates some output given the input in the placeholder variables and the model variables. We must also define a cost measure that can be used to guide the optimization of the variables. And finally, we define an optimization method which updates the variables of the model. You can also use something called TensorBoard for debugging and logging data, but we don't use that in this tutorial. So the placeholder variables are the things in the computational graph that we can replace with actual input. And the way that we define the placeholder variable for our input images is like this. So we say x equals tf.placeholder, and the data type is floating point 32-bit. And this placeholder variable is a 2-dimensional tensor, that is a 2-dimensional array or a 2-dimensional matrix. And we set the number of rows in this matrix to none, which means that it can have an arbitrary number of rows, and the number of columns in the matrix is set to image size flat because we want X to hold, for each row we want it to hold an image, which is a flattened vector of this size. For each image in X, we have a label, which is the one hot encoded class for that image. And we call this a true class, or yTrue. And again, we have a floating point placeholder variable. And now we have a matrix with an arbitrary number of rows, but the number of columns is equal to the number of classes, which is 10, one for each digit, 0 through 9. Sometimes we also need the class as a number, as a single number, instead of being one hot encoded. So we have that in yTrue class, and it's a placeholder variable, and this time it's an integer, and it can be an arbitrary length. So it's just a one-dimensional tensor or an array whose length is set to none. So now we have defined the placeholder variables, and now we need the models variables that are going to be optimized. And these are traditionally called weights and biases. So we define the weights as a tf.variable, and we initialize it to zeros. And we will see in a moment that when we matrix multiply this with X, we get the output shape that we want. So we also define the biases, and that's another variable, and it's just a one-dimensional tensor or vector of length 10 for the number of classes, and this is also initialized to zeros. It's important to mention that nothing is actually initialized or calculated at this point in time. We are just building the computational graph, then later we will start executing it. So this simple mathematical model just multiplies the images in the placeholder variable X with the weights, and then it adds the biases. So the result is a matrix of shape num images rows and num classes columns. And we will give this result the name logits because that is typical in TensorFlow. So again, nothing has been computed yet, but the idea is that logits will now, when we start computing this, it will hold a matrix which has num images rows and num classes columns. And the element in the ith row and the jth column is an estimate of how likely the ith input image is to be of the jth class. And this may be a little tricky to understand. However, these estimates are quite rough, and they might be very small numbers or very large numbers, and what we would like is that we would like each estimate to be a number between 0 and 1, and when we sum the estimates for each class of each image, we want them to sum to 1 so that we can sort of interpret them as probabilities. So we have now calculated ypred, which is for each image, it gives us a vector of length 10, and sometimes we like to have this class as a number, as an integer, so we use TensorFlow to calculate the argmax, which gives us for each vector, it gives us the index of the element that is highest. So in order to optimize the weights and biases, we need to define the cost measure. And we use the cross entropy because it gives us a continuous performance measure, and the minimum is 0. So if it's a perfect match in the classification, then the result is a 0, and otherwise it's some positive number. So what we do is that for each input image, we calculate the cross entropy between predicted classes and the true classes. And there is a little catch to this because we have to use let us go back up. We have to use logits here because if we use ypred, it has already calculated the softmax, and then it gives us the wrong results. So we need to use the logits and yTrue. This calculates the cross entropy for the classification of each input image, and we need the cost measure to be a single scalar value, so we just calculate the average of all these cross entropies for all the images. Now we can define the optimization method, and we just use the built-in gradient descent, which is the most basic optimizer in TensorFlow, and we tell it that it should minimize the cost that we calculated up here, so the average of the cross entropy of all the input images. However, again, you should note that nothing is calculated here. We're just building the computational graph. In addition to this, we sometimes need to measure the performance of how our classification is doing. So we first calculate for each input image whether it was classified correctly. So we compare the predicted classification with the true classification. And then we calculate the classification accuracy, which is just the number of correctly classified images divided by the total number of input images. And the way we do that is that we cast these Boolean array to floating point so that the false becomes 0 and the true becomes 1. And then we just calculate the mean. It's just a little computational trick. So now we are finally ready to run our computational graph. Nothing has been computed yet, and now we want to do that. So first we have to create a TensorFlow session. We do this with this command here. And now we want to initialize all the variables. So those are the weights and the biases. And we do that by running the session with this function here, tf.initialize all variables. Then we define a helper function to perform actual optimization iterations. Remember that there are 50,000 images in the training set, and it takes a long time if we were to calculate the gradient of the model using all these images. So we therefore use a batch size of 100. This is also sometimes called a mini batch size, so that in each iteration of the optimizer, we just calculate the gradient for 100 images in the training set. So the helper function for doing this looks like this. It takes in a number of iterations and then it has a for loop. And we use a TensorFlow function to get the next random batch of training images. So X batch now holds 100 randomly selected images from the training set, and Y true batch holds a true classification labels for those images. Then we have to create what is called a feed dict or a feed dictionary. And the keys in this dictionary have to match the placeholder variables that we defined above. So X is a placeholder variable for the matrix of images, and Y true is a placeholder variable for the matrix of true classification labels for those images. So here we define the feed dict, and then we say run the TensorFlow session with the optimizer, and remember that we defined this above to be gradient descent, and we feed in the data that we just set, which is the training batch. And it calculates the predicted class for all the images and the cross entropy, and it takes the average to calculate the cost. And then TensorFlow does something quite magical, and it goes back through this computational graph and calculates the gradients for our weights and biases, and this happens all behind the scenes. And then it uses the gradient descent to update the weights and biases. Okay, before we can show the results of this, we first need a few helper functions. So we need another feed dict for the test set. So we set the images and the true classification labels and the classification integers to be those from the test set. The function here prints the classification accuracy on the test set. So we just use the feed dict that we just created. And then we run the TensorFlow session with the part of the computational graph that calculates the classification accuracy. Remember that we defined this before. We can also print the so-called confusion matrix, which gives us more details about the classification errors. And we use scikit-learn for this. And this is a helper function which takes some of the misclassified images and plots them. It is also helpful to plot the weights of the model, and that is done in this helper function. So before we start optimizing the model, let's print the classification accuracy on the test set, and it shows it is 9.8%. And what happens here is that the model always outputs 0. So the model always predicts that the image is a 0, and it just happens that 9.8% of the images in the test set are zeros. So let's perform a single optimization iteration. Then the classification accuracy is 40.7%. So that is actually quite a lot just from a single optimization iteration. So let's see a few examples of where the model misclassifies the images. And in this first example, the image shows a 2, and the model has predicted that it's a 6. And in the second one, it shows a 4, but the model predicted it was a 0, and so on. So the model is still quite bad, but it only had one optimization iteration. So let's show the weights of the model, and the weights that are used to determine if the input image is a 0 looks like this. The positive weights are red, and the negative weights are blue. And we can interpret these weights as being filters on the image. So if we overlay an input image on this filter, then pixels inside this circle here have a positive reaction on whether this might be a 0 or something else. And if there are pixels inside the center of the circle, then it has a negative reaction. So this filter likes seeing circles with nothing inside. The weights that are used to determine if the input image is a 1 have positive weights as a vertical line in the center and has negative weights around that. So if we input an image here that has black pixels in the center vertical line and nothing around it, then this filter here will have a positive reaction to the input image. Now the weights that are used to determine if the input image is a 2 are more difficult to interpret. We have some slightly positive weights up here and down here, and then we have very negative weights here. So we can sort of imagine that this might be a 2, but it has actually not recognized 2s. It has recognized something like the inversion of 2s. The weights for 3, 4, and somewhat 5, 6, 7, 8, and 9, most of these are quite clear what the weights try to recognize in the input image. So now let's try and perform some more optimization iterations. We have already performed one above, and we perform an additional 9 so that we have a total of 10 iterations. And now the classification accuracy is 78.2%. And if we look at some of the classification errors, and the model now thinks that this is a 4, but in reality it's a 9. And this one, the model says is a 2, but it's a 5, and so on. Let's look at the weights again for the model. So now they're actually all of them quite clear what they're trying to recognize. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. But let's see what happens when we perform 1,000 optimization iterations. So now the accuracy on the test set is 91.5%. So this means that in 8.5%, or almost 1 out of 10 cases, we misclassify an image in the test set. So let's look at some of the examples. And here the true class for the image is a 5, but the model predicts that it's a 6. And that is sort of understandable because this is a very badly drawn 5. It could be a 6. So that's fair. And the next one, the true class is a 4. This is supposed to be a 4, but the model predicted that it's a 6. Okay, that's a bit strange. The next one, the true class is a 2, and the model predicted that it's a 3. That's not very good actually. It should be able to predict that this was a 2. And similarly down here we have another 2, and the model predicted that it was a 7. And here we have a 6, where it predicted that it was a 7. So the model is not very good actually. It really should be able to do this. And what you can try is that you can try in the exercises, you can try and execute 10,000 optimization iterations and see if it gets better. So let's look at the model weights after having been optimized for 10,000 iterations. And remember that in each iteration, we selected randomly 100 images from the training set and calculated the gradient and updated the weights and biases using these gradients for the classification errors. So now the weights that are used to classify a 0 look like this. So the strongest weights are now in the center, so that if we see black pixels in the center of the image, then it has a very negative effect on whether the model thinks that this is a 0 or not. And then we have sort of a circle surrounding that center, and those are reds. So if we see black pixels in the input image that are sort of a circle, then that has a positive effect on estimating that this is probably a 0. And the weights for classifying whether the input image is a 1 still has the vertical line, which are strong positive weights, and then we have some strong negative weights surrounding that. So that is also still somewhat clear what these weights try to recognize in the input image. But for the other classes, this is not clear at all. So this is maybe with a bit of imagination, we could say this tries to recognize 2s, and maybe we could say this tries to recognize 3s. But how about this, or this, or this, or this, or this, or this? What is going on here? It looks like the model has sort of tried to make a compromise of all the images that it has seen in the training set and say, oh, if we see pixels here and here and here, and a little here and a little here, but no pixels anywhere else, then this must be a 4. And of course, this is not at all how a human recognizes a 4. And similarly for the 5, it says, if we see black pixels in the input image up here, especially up here, and also a little here, or a little here, and a little here, and we only see white pixels here where the weights are blue, then we classify it as a 5. So I don't know. It's weird. And you can sort of, maybe if you have a lot of imagination and maybe if you smoke some weed or something, maybe you can see an 8 here or a 9 here. But I have to say, it gives the impression that the model actually doesn't really understand what is going on. It doesn't really understand how to recognize digits. So for this, we need a more sophisticated model. Now we can also print the confusion matrix, and this is actually quite confusing to look at. It may be a little simpler to look at the plot instead. So what this shows is that, for example, for the true class 5, it is sometimes misclassified as a 3 and sometimes as an 8. And I suppose that makes sense because a 3 looks sort of like a 5, which looks sort of like an 8. So after we are done using TensorFlow, we really should close the session, but I have left it open here in case you want to make changes to the notebook without having to restart it. I have also made some suggestions for exercises, and I think you should go through most of these. A lot of them are quite simple and can be done quickly, and it helps you understand better how TensorFlow works if you do it yourself. And you can download this notebook from the link below the video.